Welcome. This is Dr. Sudha, Associate Professor, Department of Mathematics, Drupatunga University. In this session, we are going to state and prove Cauchy's theorem. So the statement of the Cauchy's theorem goes like this. If P is a prime number and P divides order of G, then P has an element of order P. So if a prime number divides the order of the group, then we must show that there is an element of order P in G. So we prove the result by induction on order of G. Since P divides order of G and P is prime, then we can assume that order of G is greater than or equal to 2 because 2 is the least prime number. So order of group G must be equal to 2 or greater than 2. So since P is equal to 2 is the first prime number. So let us take order of G is equal to 2. That means G contains two elements. One element must be the identity element E and the other element is any other element A. Then A square will be equal to E. That is A is self-inverse. Since order of G is equal to 2 and 2 is even, and we know that if a group is of even order, there is an element which is self-inverse other than the identity element E. So order of A is equal to 2. That is A is an element of order 2. So order of G is equal to 2 and we have shown that there is an element A whose order is also equal to 2. Therefore, the result is true for G of order 2. So the first step is over in the induction. Now let us assume that the result is true for all groups of order less than order of G. So we are assuming that the result is true for all groups whose order is less than order of G. So we consider two cases here. If H is a proper subgroup of G such that P divides order of G. So since H is a proper subgroup, order of H will be strictly less than order of G because H is a proper subgroup. So now let us apply the induction hypothesis. That is, in the induction hypothesis, we have assumed that all groups whose order is less than order of G will satisfy the result. So H as an element A, which is not the identity element, such that A to the power of P is equal to E. Since A lies in H and H is a proper subgroup of G, G has an element A which is not equal to E such that A to the power of P is equal to E. Therefore, the result follows when we assume H is a proper subgroup of G. Now, let us assume the other way. That is, no proper subgroup of G has the order divisible by P. So, if I assume that H is a proper subgroup of G, then P does not divide order of H. So, in particular, let us take an element A which is not in center of G. So by one of the corollary, we have proved that when A does not belong to Z of G, N of A, that is normalizer of A, is not equal to G. That means N of A is a proper subgroup of G. Since it is a proper subgroup of G, by our assumption here, P will not divide order of N of A. Now let us consider the class equation which we have obtained in the previous sessions. So order of G will be equal to order of z of g plus summation order of g divided by order of n of a whenever n of a is not equal to g. Since P divides order of G, okay, and we know that P doesn't divide order of N of A. Now let us consider P divides order of G. So P must divide uh, summation order of G divided by order of N of A, where N of A doesn't is not equal to G. This is by one of the class equation which we obtained in one of the corollary. So since P divides order of G, P must divide this summation. Now P divides both order of G and summation order of G divided by order of N of A. Therefore, P must divide difference of these two. That is order of G minus summation order of G divided by order of N of A. But this quantity from this class equation will be equal to order of Z of G, because when we shift this term to the left hand side, we get order of G minus summation order of G divided by order of N of A, and that is equal to order of Z of G. So in the next step, we get P divides order of Z of G. And this implies G is equal to the center, because we have assumed that P does not divide any proper subgroup of G. Okay, so Z of G is not a proper subgroup of G. Since it is not a proper subgroup of G, it must be equal to G. Since Z of G is abelian, we can say that G is also abelian. Now let us move on to the next part. That is, if G is abelian, we know from a well-known result that every subgroup of an abelian group is normal. So if I take any subgroup of G, then it becomes normal. So let us take N to be a subgroup of G. Then N is normal in G. Since N is normal in G, we can think of the quotient group G by N. Therefore, G by N exists. So now let us consider what is order of G by N. So by Lagrange's theorem, we know that order of G by N is order of G divided by order of N. And this quantity is strictly less than order of G. So by induction assumption, order of G by N is strictly less than order of G. Therefore, G by N has an element of order P. Let us assume that element to be NB, because G by N contains only the cosets. We can say that NB is one of the coset which is not equal to E. That is, the identity element of G by N is N, such that NB will have power P which is equal to the identity of G by N. And this B will be an element of G. Now let us consider NB to the power of P, which is equal to the identity N. So when NB to the power of P means we are operating the coset NB P times. When I operate P times, that is NB into NB into NB P times, I get NB to the power of P is equal to N. Now, NB to the power of P is equal to N, which is similar to HA is equal to H, which implies A belongs to H. I can say that B to the power of P belongs to N. Now, B to the power of P belongs to N, and it is an element of N now, which is similar to if A belongs to G, then A to the power of order of G must be equal to E. So I can write B to the power of P to the power of order of this subgroup, that is order of N, is equal to E. Now using laws of indices, I can interchange this P and order of N, and I can write B to the power of order of N whole to the power of P is equal to E. So I get this expression. Now let me take this B to the power of order of N is equal to C. So I get C to the power of P is equal to E. My intention is I need to say that this is the required C. For that, C must not be equal to E. Let me show that C is not equal to E. By contradiction method, I am going to show that C is not equal to E. Let me take C is equal to E. When I take C is equal to E and consider NC, that is the coset generated by C, so that will be equal to NE because C is equal to E. And we know that NE is equal to N. So NC is equal to N now. Let me replace C by B to the power of order of N. So I get NB to the power of order of N, which is equal to N on the right hand side. And this is the identity in G by N. Now I have NB to the power of order of N is equal to N, and it is the identity in G by N. So it is similar to A to the power of M is equal to E, and A to the power order of A will divide M. So now order of N of B must divide order of N. But we have assumed that order of N of B is P. So P divides order of N. And this is a contradiction because we have assumed that N is a proper subgroup of G and no proper subgroup of G has its order divisible by P. Now we have obtained it is dividing, that is P is dividing order of N. Therefore a contradiction, which is a contradiction to our assumption that C is equal to E. Therefore C is not equal to E. And now we have C to the power of P is equal to E, and C is the required element of G whose power is P. Hence the result. Thank you.